the cool thing about the polar coordinate system is that you can graph some pretty neat things in the polar coordinate system, and it just gets some neat graphs. And so I'm just going to take you through graphing 2 cosine 3 theta. So if you remember back to the previous lecture, we had a 5 cosine theta, and that was a circle. And so if we had a 2 cosine theta, it would just be a circle. But we have this 3 in here, so we got to kind of figure out what that 3 does to our circle. And so the first thing is let's just kind of, if we go like through the first 180 degrees, let's just go ahead and figure out what 3 times each one of those degree measures is. So 3 times 0 is 0. And then we have 30 and 60 and 90. So I'm just multiplying each of these by 3. 120, 150, 180, 210, 240, 270, 300, 110, 120. Wow, I messed up on those last 2. Let me get those last 2 off of there. 110 times 3 is 330, 360, 390. We got 420 here, 450, 480, 510, and 540. So if you noticed, even though I'm going only through the first 180 degrees, in terms of the polar graph, I've made it all the way around by the time I've gotten to here on the polar graph. So what does that do in terms of my graph that I get here? So if I have the cosine of 30, then, or the cosine of 3 theta times 2, you know, then we're talking about cosine of 0 is 0. Is 1. 2 times 1 is 2. So we're looking at a radius value of 2. Cosine of 30 is the square root of 3 over 2. And so square root of 3 over 2 times 2 is the square root of 3. Cosine of 60 is a half. 2 times a half is 1. Cosine of 90 is 0. Cosine of 120, so we're talking about out here, is a half. Half times 2 is 1. So we're kind of seeing the symmetry here. And that's a negative 1. Cosine of 150, so is negative root 3 over 2, times a 2 is a negative root 3. So you can kind of start seeing the symmetry here about 90 degrees. Cosine of 180 is negative 1, times 2 is a negative 2. So let's just take a look at those first. At a theta of 0, we have a radius of 2, so at a theta of 0, we go out 2 concentric circles along the polar axis, and then at 10 degrees, we go out square root of 3. So at 10 degrees, right here, the square root of 3 is about 1.7. And then at 20 degrees, we're going to go out 1. So at 20 degrees, we should be right there on that concentric circle, r equals 1. And then at 90, we're back at 0. And then as we go to, at 30, we're back at 0. And then if we go to 40, we're at negative 1. So here's 40. And so if this is the 40 degree line, then the negative 1 line is right here. And then at the 50 degree line, we're at negative root 3. So at negative root 3, it's about negative 1.7. It's about here. So here's our 50 degree line, but the negative radius will bring us to the other side of that circle there. And then at 60 degrees, we're at -2. So if we take the 60-degree radial line to a distance of -2 or 2 in the negative direction, we're right there. So we have this sort of thing so far. And now let's do the next 60 degrees. So at 70 degrees, we're at 3 theta of 210, and so that's going to be a negative square root of 3 over 2 times 2 is a negative square root of 3. And at 240, when 3 theta is 240, cosine there is -1/2 times 2 is -1. And at 270, 3 times 270 is, 3 times 90 is 270, so that's right here. So at 270, we're back at 0. And then at 300, that would be an angle of 100. So here's an angle of 100. We had a radius of 1. And then we are at square root of 3. And I'm going a little quicker here, and at 2, because I'm more or less using the symmetry here instead of actually calculating it. So for this second portion here, we're going to be at 70 comma minus root 3. So here's 70, here's minus root 3. And then we'll be at 80 and -1. So here's 80, and here is -1. And then we're going to 90 at 0, so we're back here at the pole. And then to 100 at 1, so here's 100, and we're going out to a radius of 1. And then 110, we're at square root of 3, so at 110, we're right about here. At 120, we're at a radius of 2, so we're back into these positive radii. And now I'm definitely going to use the symmetry here, so I know this is going to be square root of 3 because of the symmetry here. And then this one is going to be a 1 again because of the symmetry. And then we're back to 0. And we have a -1 and a minus root 3 and a -2 to round it out. So if you notice then, as we keep going around here, so we're at 130 degrees and the square root of 3, so 130 and the square root of 3 is right there. And 140 and 1 is right here. And then 150 and 0 is back at the pole. And then 160 and -1. So 160 and -1 is right here. And 170 and negative square root of 3. So 170 and negative square root of 3 is right here, about -1.7. And 180 -2, so 180 -2. And so you notice with that last point we made it back to where we started again. And so this allows us to trace the shape once. And so when we color this in here, we have, if we colored it in, it would look like this. And then it came down here, and then it went up here, and it came over here, and created this, and then it looped back. And so we went through the pole several times, and we ended up getting something like this. And we call this a 3-petal flower. People call it, in general, it's called a rose petal. And so if we take a look at the fact that it has 3 petals, that's because we see the 3 here. If we take a look at the fact that the petal is 2 concentric circles long, or has a radius of 2, that's how we find the length of the petal. So we can see those characteristics just in the equation. So in this situation, and the reason why I'm spending so much time on this is because when we get to graphing them, what we're going to be doing is we're actually going to be finding like the area inside the petal and stuff like that. So that's kind of where this is taking us in that respect. So, and then we're also going to deal with things like finding tangent lines and stuff like that, like what's the tangent line at the petal at this location here or this location here. The tangent line here, of course, would be vertical. So we're going to take a look at all of those aspects of creating these petal graphs, these rose petal graphs. When we take a look at the Cartesian derivative dy dx, and that is the definition of the first derivative, we have to acknowledge the fact that when we have things like rose curves or petal curves, that these are written in terms of r and theta. So we have to then get that into its Cartesian form before even thinking about taking the derivative. So we need to remember that we have our conversion as to get to x, we do our cosine theta, and to get the y, we do our sine theta. And so these are here, then these are Cartesian functions in parametric form. So then we can do a dy d theta divided by dx d theta to get the definition, the Cartesian definition of the definition of the Cartesian coordinate dy dx. And so that is kind of what is being said right down here in terms of let's get the parametric form. And I like to kind of stop with that definition. This if we take a look at this, and we can kind of see it if we use this this rose petal here, the r equals 2 cosine 3 theta. If we look at r equaling 2 cosine 3 theta as our polar function, then in order to get this in Cartesian form, we have to do this. So if you notice, then our x is going to be this cosine theta, so 2 cosine 3 theta times cosine theta, and our y parametric is going to be r, which is this, times sine theta, so 2 cosine 3 theta times sine theta. And so these are our parametric equations. So those are these for the curve above. And so if you notice, to take the derivative of this and to take a derivative of that, we're going to need the chain rule. And that's what this is all here. This is just doing the chain rule on the parametrics. And if you want to memorize that, you can. I'm not a big fan of memorizing, but if you notice, it's f cosine theta plus f prime sine theta. So if we look at this, this is function times the derivative of sine, and then derivative of function times sine. So this top here is derivative of this times that plus the derivative of that times this. So it's just the chain rule. And the bottom is the derivative of this, which is minus sine, times that, times the derivative of that times this. So those are just the chain rule expressions. I would rather, I think it's easier for us to just get our Cartesian parametrics and then take the derivative of this and stick it in the numerator, and take the derivative of this and stick it in the denominator without a whole lot of thought to this equation and knowing it. It comes when you just do the derivative correctly. So let's take a look at this example here. We have a polar equation that says r is equal to 2 plus 2 cosine theta. We want to graph it from 0 to 2 pi. So the nice thing with our graphing calculator is we can really, we have these several modes, and we used the parametric mode a little earlier this chapter. We're going to go ahead and use the polar mode and get a graph of this. So once we change this, the mode to polar, if you notice, then instead of y1, or in terms of parametrics x1, y1, we've got r1. And so let's go ahead and graph our shape in polar form. And you got to kind of remember that from a Cartesian standpoint, a lot of these aren't functions. These pedal curves don't pass the vertical line test. So they're just, we just call them curves. So 2 plus 2 cosine theta, and yes, now our variables are in terms of theta here. And we're going to graph that from 0 to 2 pi. So we're going to go ahead and graph that. So we have something that looks like this. And so if we zoom on that, in fact, let's not zoom, we'll just do a window here. So we're going from 0 to 2 pi, and our Cartesian window, we can go from like, let's go from -1 to 5, and from -5 to 5. So taking a look at that window, we have that. So we have this thing that kind of looks like a circle or an ellipse with a dent in it. I'm going to square out this window just to see what it really looks like on a square grid. So there we go. So it looks like this with a little bit of a dent in it, and we'll get to what that's kind of what the name for that is when we kind of finish up this series of slides here. But you know, if we look at this, I think it looks kind of like an apple or something like that, or a tomato. And so if I kind of blow this up here and try to match the grids, there we go. And then I can kind of, looks pretty good. There we go. So if I put that, then I can kind of superimpose it on the existing grid. We have something that looks like that. And so it says find the points of horizontal and vertical tangency to the curve. So by inspection, you can see that we have points of vertical tangency right here and here and here. So we can draw our vertical tangent lines. And if you notice, this vertical tangent line and that vertical tangent line are going to be two of the same lines, just two different points on that line. And that vertical tangent line is there. And then we have some horizontal tangents here and here. And it's not uncommon for these points to have a sharp discontinuity. So there's a discontinuity right here where this curve comes into the origin and then bounces back out again. So at the origin here, we have a tangent line that might go something like this, and a tangent line that might go something like that. So those aren't horizontal and vertical, but we've got two different tangent lines, and those correspond to two different theta values. And so if we're talking about the points of horizontal tangency and points of vertical tangency, horizontal tangency is a slope equal to 0. Vertical tangency is a slope that is equal to an undefined expression. And so when we look at our Cartesian derivative and rewrite it in parametric form, we can, I think, pretty easily see that horizontal tangencies, where this is 0, that's a dy d theta equal to 0. And vertical tangencies, where this is 0, is a dx d theta equal to 0. So when we break this up into parametric forms, this situation kind of falls into place really nicely. So let's take a look at our horizontal tangencies. So we're looking at getting our parametric equation of this polar equation. And so we're looking at using the definition of y equals r sine theta. And so we have our parametric Cartesian equation is 2 plus 2 cosine theta times sine theta. So that is our function. And it's Cartesian because it's a y equals. It's in parametric form. It's in terms of theta. And so as we then take the derivative of that, we have, if we want to take the derivative of this, we can just say the derivative of the first times the second. So our dy d theta is, let's take the derivative of this. So the derivative of this is 0 plus minus 2 sine theta. So minus 2 sine theta times sine theta plus this 2 plus cosine theta times the derivative of that, which is cosine theta. So we end up having a derivative that looks like minus 2 sine squared theta plus 2 cosine theta plus there's a 2 here, 2 cosine squared theta. So we end up having a relationship that looks like that. And so the question is then, is these horizontal tangencies are points where that is equal to 0. So as we look at this expression here, we can kind of start to see we have some trig components here squared, and don't get fooled into thinking this is a trig identity equal to 1 because we have a minus sign here. So what we really need to do is we need to substitute out this sine squared theta. So this is really minus 2, 1 minus cosine squared theta, and then 2 cosine theta plus 2 cosine squared theta. Okay, we've got 2 cosine squared theta minus sine squared theta, not a trig identity. We can't make that equal to 1 times 2. So we have to go after this and see if it's a factorable quadratic. So we have a minus 2 here plus 2 cosine squared theta plus 2 cosine theta plus another 2 cosine squared theta. So when I combine my like terms here, I have 4 cosine squared theta minus 2 cosine theta minus plus minus 2 there. And then when I factor out a 2, I've got 2 cosine squared theta plus cosine theta minus 1. And this is factorable. This is like 2u squared plus u minus 1. And so that factors into 2 cosine squared theta minus 1 and cosine, I said that wrong, cosine theta plus 1. This is not a squared. This is just a cosine theta. There we go. Cosine theta. So let's just quickly check this. 2 cosine theta times cosine theta is our 2 cosine squared. 2 cosine theta times 1 minus 1 times cosine theta is a cosine theta, and then negative 1 times 1 is 1. And so that is what's equal to 0. And so if we take these then, 2 cosine theta minus 1, set it equal to 0, we have a cosine theta equal to 1/2. So there's our first location. And then we have our cosine theta plus 1 equals 0. So it's the other factor that's equal to 0. So that's a cosine theta equal to -1. Now we're graphing this over 0 to 2 pi. That was our initial condition here. So where is cosine equal to -1? That's when theta equals pi. And where is cosine equal to half? Cosine is equal to a half over here in the first and the fourth quadrants. So that is when a theta is equal to pi over 3 and 5 pi over 3. And so you notice that I get 3 solutions. I've got 2 things drawn here, so that gives me an inclination that maybe I was wrong about these tangents in the blue, that in reality this might come in so perfectly tangent at the pole that we might actually have a horizontal tangent here. That's an indication that that might be the case there. So let's go ahead and trace this and see what we get. So if we trace this, go all the way back to here's a theta of 0, and then we're stepping here by pi over, looks like pi over 12. So it's 1 pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12. 5, 6, 7, 8 pi over 12. No, I think I did that wrong. Let's see, what are we counting by? Let's see, that is 0.13, so that is pi divided by 12. No, we're counting by pi divided by 24. Pi divided by 24 is 0.3108. So when we look at this and trace it, here's 0, 0.3108. We're counting by pi divided by 24. So there's 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 pi over 24. That's our pi over 3. So that's this one. Okay, then if we come back here and continue to trace, so it's not up 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 pi over 24. Let's take a look at what we have here. 21, 22, 23, 24. There we are. So we're just getting right into that pole. So if we notice we're at the pole at pi, so that must be that solution. And then we're going for this horizontal tangent now. So we got 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. So there's our 40 pi over 24, which is our 5 pi over 3. So there's our 3 horizontal tangents. Okay, and then now we can go back and look at our vertical tangents. We know we should have 3 as well. So if we go back and look at our vertical tangents, we're looking at our x, and our x parametric is defined as our cosine theta, and so that is going to be 2 plus, that's going to be 2 plus 2 cosine theta times cosine theta. And so when we go ahead and take the derivative dx dt of that, let's take the derivative of this, which is minus 2 sine theta. So we have minus 2 sine theta cosine theta. And then we have plus the derivative of this, which is negative sine. So then we have 2 plus 2 cosine theta times the derivative of this, which is negative sine theta. So when we're looking at that, then as we simplify this, we have minus 2 sine theta cosine theta. And then we have, when we distribute this, we've got minus 2 sine theta and minus 2 sine theta cosine theta. So as we combine these, we have a minus 4 sine theta cosine theta minus 2 sine theta. So we can just factor out then a 2 sine theta, a minus 2 actually sine theta. And that's going to leave us then with a 2 cosine theta plus 1. So, and we're wondering where that is equal to 0. This being the lower portion or the denominator of the parametric, that's going to be our undefined tangencies or our vertical tangencies. So minus 2 sine theta equals 0. That gives us a sine theta of equal to 0. And 2 cosine theta plus 1 equals 0 is going to give us a cosine theta equal to negative 1/2. So over that same 2 pi interval, we're looking at where's the sine equal to 0, and that's going to be at 0 and pi. And then where's the cosine equal to negative 1, that's going to be over here. So that's going to be our negative 1/2, excuse me, I said that wrong. That's going to be our 2 pi over 3 and our 4 pi over 3. So 2 pi over 3 and 4 pi over 3. So those are those two points of tangency. Now you notice in the sketch up here, we've got 1, 2, 3 points of vertical tangency. So the question is, why do we have 1, 2, 3, 4 solutions? So let's go back and trace this again. So I'm just going to go ahead and regraph it and hit trace again. And let's see where we are. So we're back at 2 pi here. I guess I got to go backwards. So let's kind of go backwards here and start back at 0. Okay, back at 0. So we're 2 pi over, we're counting by 1 over 24. So this is going to be 16 over 24. So let's see where that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's that point of tangency. That's that upper one. So we've got that. And this is going to be, this is 4 pi over 3. This is going to be 32 pi over 24. So this is, we're at 16 here. So 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So that's that other point of tangency. So we've got that one. And so this is going to be, so if we notice, I kind of shot over 24. So if we kind of come back here, that was 32, 31, 30, 29, 28, 27, 26, 25, 24. So this one is at pi. So we've got to take a look at then this. And of course the 0, the point of 0, or when sine is equal to 0, that's at the beginning. So that's this point of tangency right there. So we got that one right at the beginning. So if you notice, we've got this right here, and we can kind of see it here as well. We've got the same solution here. So what's happening in that situation? Both are solutions for horizontal and vertical points of tangency. What does that mean from a parametric standpoint? If we look at the parametric form of the derivative, the dy over d theta divided by dx over d theta, what it's saying is at pi, we have 0 over 0. And that is undefined. So what's happening, if we take a close-up shot of the pole, in other words, the origin, so there's our origin. From the top, we're coming in like this, and it's literally coming to a point here, and we're coming back out again. So the question is, in this location right here at the pole, is this a horizontal or is this a vertical tangency? And the answer is we don't know. So it could be a horizontal. It could be a vertical. I'm trying to color code here. You know, we have both, really. And if we have both, then it's really impossible to determine if it's one or the other. So that being the case, we have to come back and we have to eliminate that as a possible solution. We just are not sure if it's a horizontal or a vertical. So that gets eliminated, and then that leaves us with our 1, 2, 3 vertical and our 2 horizontal that we know for sure. So this one comes back then and gets eliminated as a possible horizontal tangent. So there we go. This page is just to kind of familiarize you with the different shapes. These dimpled ones are typically called cardioids or limicons, and so these ones with the loops are also called limicons. And so as we can see, they kind of take on this general form. The cardioid is basically the degenerate version of a limicon where it doesn't have the inner loop. And so if we look at our previous example, it's that variety. It's 2 plus 2 cosine theta. So it's a constant plus or minus a coefficient times cosine or sine theta. So, so that's one variety. Then we have what we call the rose curve family. And so that's the a cosines and a sines thetas. And so when n equals 3, it has 3 loops. If n equals 4, it's got 8. So if the petals are odd, then there's that many petals. If n is even, like a 2 or a 4, then there's twice as many petals. And then the last thing is circles and lemniscates. So circles you're very familiar with. We've talked about those before. Lemniscates, I always think of lemniscates as something that rhymes with figure eights. So that's how I know what lemniscates look like, is they look like figure eights. And so now we're starting to put a power on this coefficient here. So just to show you the varieties of curves that we can graph in polar form pretty easily.